Now we will study about the radial wave function for the hydrogen atom. So as we know, the Schrodinger equation for the wave function of the electron that is present in hydrogen atom. Here it is the nucleus, and here it is one electron. Nucleus, there is one proton, and here it is one. So this is the wave function, equation of the wave function for this electron. Having energy capital E, having potential energy small capital V, and this is the mass of the electron, and psi is the wave function. What is psi? Psi wave function. So this is the Schrodinger equation in terms of the Cartesian coordinates. We all know that Cartesian coordinates are in terms of the axis x, y, and z coordinates, and here del square psi is the partial derivative double of the second order, and it is of the form dou 2 psi by dou x square plus dou 2 psi by dou y square plus dou 2 psi by dou z square. Now polar, if we want to solve this equation, Schrodinger equation, if it is written in the form of Cartesian coordinates only, then it is very tedious to solve it. So what is advisable is to convert it into the polar coordinate form. Means we are using now the coordinates r, theta, and phi in this equation in place of x, y, and z. Means we are changing Cartesian coordinates to the polar coordinates. So if we are converting it to the polar coordinates, then it is needed to know the relationship between the Cartesian coordinates and the polar coordinates. How we will replace x and y and z. So let us draw the axis. Here it is the x-axis. This is the y-axis, and this is the z-axis. Here is our electron, which is at a distance r from the origin. And this r is making angle theta with the z-axis. So if we draw perpendicular here from this point on the z-axis, that distance comes out to be r cos theta. So we can replace z by r cos theta. As theta will change, then r cos theta will also change. So now how to find the relation between the polar coordinates and y axis and z axis also. So let us draw one perpendicular from this point on the xy plane. So this is here our xy plane, and we are drawing perpendicular from this point on this plane. So as you know that this z-axis is perpendicular on the xy plane. You can see here. So this one distance comes out to be r sine theta. This is r sine theta, and if this uh, line is making angle phi with the x-axis, then along x-axis, this distance comes out to be r sine theta cos phi, and along the y-axis, the distance comes out to be r sine theta sin phi. So we will replace z by r cos theta, y by r sine theta sin phi, and x by r sine theta cos phi. So let us change our Schrodinger equation in terms of the polar coordinates. So it is dou dou r square dou psi by dou r plus 1 upon sine square theta, dou 2 psi by dou phi square plus 1 upon sine theta, dou theta of sine theta, dou psi by 2. So now the solution of this equation is of the form psi is equal to r theta, theta phi phi. Yeah, RR is the radial function depending on the distance of electron from the nucleus. RR is called the radial function. And it depending on distance of electron from the nucleus. And it depends on the quantum numbers n and l. On n and l. These two are the quantum numbers. Now, what is theta theta? It is the angular function of theta. Angular function of theta, which depends on the depending on the quantum numbers. And L and M, and phi is the angular function of phi. Phi is the angular function of phi. Function of phi, which depends on the quantum number M. Depends on quantum number M. Now the equation for psi can be written like RR theta theta phi. And we can write it in terms of radial part and the angular part, which is a function of M and L. Radial part is function of R and angular part is the function of M and L, where these two are the quantum numbers. The radial part, wave function, and AML is the angular part of wave function shell. Shell. R depends on NL, N and L. Angular part depends on M and L. Now we will see the radial wave function We will discuss radial wave function in detail. It is, if we see RR is a function, radial wave function, it has no physical meaning as such. But if we take the square of that, R square, now it denotes the probability of finding electron in a small volume dV near the point at which R is considered. What it gives? It is a measure of the probability of finding finding electron electron in a small volume near the point at which is considered. Or in other words, we can say that it describes the likelihood of finding an electron at a specific distance from the nucleus, irrespective of its direction or the angle. Means it is independent of the direction or the angle. It depends only on the distance from the nucleus, and the square of that, square of R, gives the probability of finding the electron at a specific distance from the nucleus. Now, radial probability density radial probability density, that is the radial part at a given point, is R square. And it is representing the probability of finding the electron per unit volume at that point. And it is obtained, how it is obtained? It is obtained by integrating the probability density. Okay. R square is found by integrating the probability density over all angles, resulting in 4 pi R square, capital R square. This is the radial probability density, and it is obtained by integrating the probability density over all the angles. So ultimately what is done, this is how we want to see how this is calculated. Now to calculate it, we are multiplying the radial probability density, means R square, is multiplied by the surface area, means R square into the surface area. Area of a spherical shell. And what is surface area of a spherical shell? That is 4 pi r square. And it's comes out to be 4 pi r square into r. So we will see the probability density, how it varies with the r, means distance from the nucleus. So first of all, we will see for the 1s orbital. 1s orbital of the hydrogen atom. Now this is for hydrogen, this is the ground state. This is the ground state of the hydrogen atom. So the probability density will be highest at the nucleus and decreases exponentially with increasing distance. The radial probability density is maximum at r is equal to a0, where a0 or a naught is the Bohr radius. Bohr radius. So probability density is maximum at r is equal to a naught. If we are drawing for the hydrogen atom, probability density is here on the y-axis 4 pi r square. This is the probability density and this is r in angstrom. So for hydrogen atom, if we take this as 5 and this as 10 for 1s orbital, this graph, if it is like 4 here, it is 8 here, the graph comes out to be like this. Here we can see that at a particular distance from the nucleus, the probability density is highest and then it decreases. As the distance increases, it decreases. And first of all, it was 0. At 0 distance from the nucleus, the probability density is 0. Means at the nucleus, if electron, we are considering electron at the nucleus, that there is no probability of finding the electron at this point. Then as you go to the distance where 1s orbital is located, here we will have the maximum probability of finding the electron. This is indicated by this maxima in this graph. So this is equal to this probability density, that is equal to the hydrogen atom radius, like this distance is A naught. Similarly, for the 2s orbital, we draw for the 2s orbital. Then 4 pi r square we write it like 1, 2, 3, 5, it is 10, then maximum at about this point. This graph comes out to be like this. So where the probability density is minimized, there I can say that here it is a node. This is called a node. So the higher orbitals means 2s and 3s, they can have the radial nodes. These are the positions where the probability of finding the electron is zero. At this point, like at this point, and number of radial nodes is equal to number of radial nodes, that is equal to n minus L minus 1. So for 1s orbital, if we can find out n minus L minus 1, comes out to be 1 minus 0 minus 1, that is 0. This is for 1s. And for 2s, n is 2, L is 0, and 2 minus, so number of nodes is 1. That we can see here that there is one node at which the probability density becomes 0. So this is the probability density function for the 2s orbital of hydrogen atom. And similarly for, we can draw for 3s. Zero, 1, 2, 3. This is the probability density. And here it is 5, 10. This is 2p. Here also we can see that number of nodes is 0 here also. And then for 3s, if we draw it for 3s orbital, we will find that number of nodes is n minus l minus 1. So for 3s, it is 3 minus 0 minus 1, that is equal to 2. So there should be two nodes that we will see. The graph shows the two nodes. That means that 2 points where the probability of finding the electron is 0. Like this. So here there are two nodes. One is this and one is this. Similarly, for 3p, here it is number of nodes is n minus l minus 1 is equal to 3 minus 1 minus 1, that is 1. So there is one node here. Now 3D. This is for 3D, where number of nodes n minus l minus 1 is equal to 3 minus 2 minus 1 is equal to 0. So no node is present here. Now, what is most probable radius? The most probable radius is the distance r, where the radial distribution function attains its maximum value. And this is found by differentiating the radial distribution function with respect to r and setting it to equal to 0. Okay. So radial the most probable distance It is the distance r, where the radial distribution function attains its maximum value is found by differentiating the radial distribution function with respect to r and setting it to 0. 0. What is the radial distribution function? Radial distribution function is is 4 pi r square, and this is equal to, and it is the probability of finding an electron at distance r from the nucleus. Now we had drawn so many diagrams for the different orbitals 1s, 2s, 2p, 3s, 3p, 3d. And here, from here, we can see from these diagrams, some points are revealed. These are the, we can summarize these points as, first of all, probability is 0 at the nucleus. Probability 0 at the nucleus. Means at the nucleus, the probability of finding the electron is 0. And there is no possibility of finding an electron at the nucleus. And the most probable distance increases markedly. Most probable distance means the distance at which the probability is maximum. This is the most probable distance. It increases markedly by the as the principal quantum number increases. Second point is that from the plots that we have discussed here for the 1s, 2s, 2s and 2p, 3s, 3p and 3d, means for 2s and 2p, we have discussed the plots for 2s, 2p and for 3s, 3p and 3d. Here the principal quantum numbers are same in this case, and here also the principal quantum numbers are same. So in both the cases, the most probable radius decreases slightly. Most probable radius decreases slightly as the subsidiary quantum number increases. Subsidiary quantum number means L, the value of L. Third point is that all the s orbitals except the first one, that is 1s, and um, these have a shell-like structure with concentric layers of electron density. All s orbital except 1s. That's all s orbitals except 1s means 2s, 3s, like that. They have a shell-like structure. Shell-like structure with concentric layers of electron density. And for in case of p orbitals, all except the p orbitals 2p all except the first p orbitals 2p, and this is the first p orbital 2p, and the first d orbitals, which is the first d orbital, that is 3d, they have a shell structure. Now you can see from the diagram the structure is the nature of the curves that these points we have noted. Now it is all about the radial wave functions. Thank you.